Hello, welcome back. In this video, we'll discuss the lasing action. The lasing action involves components and various elements. We need a pumping source, we need an active medium, we need population inversion to occur in the active medium, we need stimulated emission of radiation, after which the amplification of light takes place. The amplified light will move back and forth in an optical resonator. Later, from the optical resonator, we get the laser. Please note that laser is a light amplifier. Laser is also referred to as a light amplifier. We shall try to understand the lasing action with the help of a conventional electronic amplifier, that is an audio amplifier. This is the block diagram of a public addressing system. In this, you have an amplifier circuit, and the amplifier circuit will have the active elements. In electronics, the transistors are called as active elements. The required amplification essentially is done by the active elements, that is the transistor in the case of an audio amplifier. And to drive the amplifier, you need a DC power supply. So this is the power supply. The amplifier draws power from the DC power supply and amplifies the signal. This is the input. We have the input signal that is represented here, and the small input signal, after amplification, its magnitude is increasing. So this is what essentially happens in the case of an audio electronic amplifier. While in the case of lasers, no external signal is given. A photon is generated within the laser in accordance with the design and structure of the laser, and that photon will be amplified. Now we shall discuss the steps involved in lasing action. The first step is you need a pumping source. Just similar to the audio amplifier, which requires a DC power supply, the laser also needs power, and that power source is called as the pumping source. Pumping source essentially is a source of energy that is used to pump energy into the active medium. We need to supply energy into the active medium. For that purpose, you need a pumping source. Like the way we drive the transistor into the active region by suitably biasing the transistor with the help of a DC power supply. Here, we'll have an active medium in which the amplification takes place. To drive the medium into an active medium, you need to supply certain amount of energy. The source of that energy is called the pumping source. The atoms in the active medium are in their ground state initially. By supplying energy from an external source, the atoms are excited from ground level to an excited level. Active medium. Just similar to the way we have the transistors that are active elements in an electronic circuit, here also we need a medium that could be a gas or a liquid, a solid. Within the active medium, we can have the metastable states. While discussing the three quantum processes, we have said that the electron that has gone to the excited state will remain there for a very small duration, which is called as the lifetime. We have also said that the lifetime will be about 10 power minus 15 seconds or 10 power minus 12 seconds. There will be some excited states whose lifetime is considered to be very large, maybe in 10 power minus 6 seconds or 10 power minus 3 seconds. So such a time is very, very large on the atomic scale. Earlier we have seen lifetimes of excited states that are 10 power minus 15 or 10 power minus 12. Now we have lifetimes in the active medium for some of the excited states that are 10 power minus 6 or 10 power minus 3 seconds, which means these set of energy levels in the active medium have a very large lifetime, and such states with very large lifetime are called as the metastable states. The metastable states in the active medium are responsible for the lasing action. So active medium is a medium in which the population inversion can take place, or it is the medium in which light amplification happens. Now we shall see the population inversion. The lifetime of atoms in the excited state is extremely small. So the atoms that have gone to the excited state, they drop spontaneously from the excited state to the lower energy levels. And if the lower energy level happens to be a metastable state, the lifetime of the atoms at the metastable state is comparatively longer, maybe 10 power minus 3 seconds. The atoms go on accumulating at the metastable state because we are supplying energy so that the electrons goes to the excited state, and from there immediately they drop down to some intermediate level which we are calling as metastable state, whose lifetime is quite large. So the accumulation of the atoms in the metastable state continues as long as you supply the energy through the pumping source. So as soon as the number of atoms in the metastable state exceeds that of the ground state, the medium goes into what is known as a population inversion. This kind of a diagram we have seen while discussing the Boltzmann distribution. The population of various electronic states under thermal equilibrium in an atomic system will be like this, where the lower energy levels are highly populated. As you go up in the increasing energy direction, you notice that the population of the higher energy levels coming down before supplying the energy or before pumping. And when you start pumping the energy, the atoms in the ground state, their number slowly decreases because the atoms, they go to the excited state. Say we supply some energy that is sufficient enough to pump the atoms into E2 energy level. From ground state, atoms would go to the E2 excited state. Since E2 excited state is a normal state, the atoms, they keep dropping to the lower energy level, that is E1. This is E1. This is E2. Due to a spontaneous process, they drop to E1 energy level, where E1 energy level is a metastable state. From ground state, we are sending the atoms to the E2 energy level. From there, they immediately drop down to energy level E1. E1 is having a very long lifetime. The population of E1 state keeps on accumulating. So the population of E1 state increases, the population of the ground state decreases, and the population of E2 fluctuates. Now here we have a peculiar situation. Under thermal equilibrium, before pumping the energy, the population of the ground state is quite large, and all the higher energy levels, they are less populated. When you pump the energy into the lasing medium, we notice a situation where energy level E1 is having higher population than the ground state. This is what is called as population inversion. Metastable state will have a greater population than the ground state or the lower energy levels. The stimulated emission. The stimulated emission is responsible for the amplification in lasers. We shall recall that stimulated emission is a downward transition process. In order to have a downward transition to take place, you need to have the electrons in the excited state first. In lasers, the stimulated emission happens between the metastable state and other lower energy levels. Suppose 2 photons are falling on a material in which 5 electrons are in the metastable state, and these 2 photons, they can trigger the downward transition of 2 electrons. As a result, you will have 3 electrons left in the excited state and 4 photons coming out of the medium. And after the emission process, we are left with 3 electrons in the excited state and 3 electrons in the ground state. A single photon, upon interacting with an atom, it multiplies into 2 photons because the single photon moves as it is. Another photon is a resultant of a stimulated emission. This photon can trigger one more downward transition. Similarly, this one also can trigger another downward transition. These 4 photons now can trigger another 4 stimulated emission processes, giving rise to 8 photons. So we have started with 1 photon and now we have 8 photons. So like that, amplification takes place in the case of lasers, and this happens due to the stimulated emission process. This is the rough structure of a laser. You will have one mirror here. This is a semi-transparent mirror, and on this side you will have a reflecting mirror. You have the active medium that contains the active centers, that is the host material, and under non-excited condition, all atoms in the active medium, they will be in the ground state. In this case, the pumping source is an optical pumping, means we are letting light to fall on the active medium such that the atoms in the active medium, they can be excited or they can go to the higher energy levels. After that, a photon is released from a metastable state to a lower energy level. This photon, if it can satisfy the oscillation conditions of the resonator, then that photon population increases, while the other photons that are released in the other directions, they will be moving away from the active medium. Those photons that are moving in other directions, they do not contribute to the lasing. Only those photons which can establish sustained oscillations between these two mirrors can only contribute to the lasing. And light amplification takes place when this photon interacts with the other atoms in the metastable state. After undergoing several oscillations, the light eventually comes out of the partially transparent mirror. We shall now look at the optical resonator. An optical resonator essentially is a box with one fully reflecting mirror and one partially reflecting mirror. And this box or the optical resonator is essential to increase the photon density of the desired photons. There are several structures for the optical resonators. The first one is plane parallel resonator, where two mirrors are parallel. One is partially transparent, the other one is fully reflecting mirror. Concentric resonator, you have curved mirrors in this fashion. And confocal resonators, they will have mirrors like this. And ring resonators, where the mirrors are in the form of a ring. Oscillations. Within the optical resonator, one can see the oscillations taking place. What are these oscillations? Let us see. At each reflection at the front end mirror, light is partially transmitted, because you have a partially transparent mirror, and the transmitted component constitutes a loss of energy from the resonator. When the losses at the mirrors and within the medium balance the gain, a steady and strong laser beam will emerge from the front mirror. At each reflection at the front end mirror or partially transmitting mirror, light is partially transmitted through it. The transmitted component constitutes a loss of energy from the resonator. When the losses at the mirrors and within the medium balance the gain, a steady and strong laser beam will emerge from the front end mirror. That is how the lasing takes place in the case of a laser. In this video, we have started our discussion with a comparison between electronic audio amplifier and a laser. We have seen what a pumping source is. We have said it is a source of energy that is used to pump energy into the active medium. We have seen what the active medium is. The active medium could be a gas or a mixture of gases, a liquid or a solid. The active medium will have the metastable states. The metastable states are those energy states whose lifetime is very, very large when compared to the rest of the energy states in the same medium. We have seen what is population inversion. We have seen the stimulated emission process. We have seen how the stimulated emission process enables the lasing. We have seen the resonators. We have seen the oscillations and how they happen in the case of a laser. Thank you.